Welcome back to QHSE Talks.
It's great to be here.
Yeah, and right now, think about this. You are sitting in a room surrounded by literally thousands of pounds of fuel.
It's true.
The chair you are sitting on, the desk in front of you, the clothes on your back, the drywall. And on top of that, you are submerged in this invisible ocean of oxygen.
Right, which we completely take for granted.
Exactly. And the only thing standing between your current peaceful reality and a catastrophic life-ending fire is this microscopic chemical chain reaction.
A reaction that lasts for a single millisecond.
Just 1,000th of a second.
Yeah.
I mean, that is just a razor-thin margin of safety.
Okay.
And it governs our entire physical world.
It really does.
So today, we are cracking the code on that margin. Because this QHSE Talks kicks off a brand new series covering Domain 4 of the Associate Safety Professional exam.
Which is fire prevention and protection. And it is a phenomenal place to start our new series. Because, for anyone sitting for the ASP exam, Domain 4 weighs exactly 12% of your overall score.
That is a huge chunk.
It's a massive, critical chunk of the blueprint. But honestly, more importantly, taking the exam out of the equation for a moment, this is the absolute bedrock of life safety.
And that is the crucial point I want to make to you, the listener, sitting right here at the table with us.
Yeah.
This isn't just about passing a test, right? It's not about memorizing some flashcards so you can bubble and see on a screen.
No, not at all.
Understanding these absolute fundamentals is a non-negotiable skill. You need it as a safety professional to effectively perform your daily life-saving duties.
Because if you don't understand the primal nature of fire on a molecular level, you simply cannot protect your people.
You just can't.
You are dealing with physics and chemistry, and physics and chemistry do not care about your company's safety policy.
They really don't.
You cannot engineer a safe facility or, write a hot work permit or implement a successful emergency response plan if the underlying mechanics of combustion are a mystery to you.
Right. It would be like trying to design an airplane without understanding gravity.
That's a perfect way to put it.
So the mission of this QHSE Talks is to unpack those exact mechanics. We are pulling directly from ASP blueprint materials, the BCSP, CSP preparation questions, OSHA guidelines, and foundational industrial hygiene texts.
The heavy hitters.
Yeah, the real deal. We are stripping away the assumptions and looking at the absolute fundamentals of fire science.
From fire classification to the fire tetrahedron.
Right, and flammable limits. Because fire is dynamic. It's almost like a living organism that responds to changes in temperature and pressure.
It adapts.
It does.
And before you can prevent an environment from initiating a fire or extinguish one that is already raging across a factory floor, you have to know exactly what you are fighting.
So we need to deconstruct the chemical anatomy of combustion itself.
Let's do it.
Okay, let's start with what we all learned in grade school. For decades, the safety industry, and really just culture at large, relied on the fire triangle.
Right.
You gather around the campfire, and you are told you need three things: fuel, oxygen, and heat.
The classic triad.
Right.
And to be perfectly clear, that model is still technically accurate.
Oh, it is?
Yes, but only for a very specific type of fire. We call it glowing combustion.
Glowing combustion.
Yeah, this is combustion that happens entirely at the surface of solid fuels.
Okay, so like the glowing embers of a charcoal grill.
Exactly.
Or a log that is burned down to red-hot coals in a fireplace.
That's a great visualization.
Oh.
In those embers, you have your fuel, which is the carbon matrix of the charcoal or the wood.
Right.
You have the ambient oxygen in the air slowly interacting with that surface. And you have the radiant heat that initiated and is slowly continuing the process.
But there's no actual flame.
Right. The reaction is happening, but it is slow, surface level, and doesn't produce a visible flame.
Got it. But safety professionals aren't usually getting called in the middle of the night for glowing embers.
No, they are not.
We are dealing with roaring industrial fires, visible flames that can consume a warehouse in minutes.
And here's where it gets fascinating.
Okay.
When we talk about a visible flame, the safety industry had to physically evolve its mental model.
Meaning we had to ditch the triangle.
We had to move from a flat, three-sided triangle to a four-sided, three-dimensional shape.
The fire tetrahedron.
Exactly. The fire tetrahedron or the fire pyramid.
Yeah.
We had to add a fourth dimension to our understanding because a visible flame behaves entirely differently than a glowing coal.
Okay, so what is that fourth dimension?
To produce a visible flame, And more importantly, to sustain that aggressive, rapid fire, a fourth component is absolutely required.
And that is
an uninhibited chemical chain reaction.
Let's pause here because this is where a lot of people just glaze over when they read the manual.
Sure.
We have fuel, oxygen, and heat to initiate the fire. But to sustain a visible flame, we need this chain reaction.
That's right.
So is the fire triangle essentially like gathering the raw ingredients for a cake, while the fire tetrahedron is the actual chemical reaction of the cake baking in the oven?
I love that analogy.
Because you can have flour, eggs, and sugar sitting in a bowl on the counter. They're the ingredients.
Right. But they aren't a cake.
Exactly. They aren't a cake until you introduce the heat, and the chemical transformation begins to fundamentally alter the molecular structure of the batter.
That perfectly separates the potential from the kinetic.
Okay.
The triangle is your prerequisite list. It's the hazard potential sitting on the counter. The tetrahedron is the active, ongoing, violent event taking place in the oven.
Wow. Okay, so if we zoom all the way in on a molecular level into the oven of that analogy, what is actually happening inside that flame?
It's a continuous looping cycle of oxidation and reduction.
So break that down for us.
Yeah.
What is actually tearing apart inside the flame?
Okay, so when you apply enough heat to a solid or liquid fuel, it begins to vaporize. It turns into a gas. Fire only burns in the vapor phase, so these fuel vapors mix with oxygen. The intense heat causes the bonds of the fuel molecules to physically break apart.
Like shattering them.
Basically. And as they break apart, the fuel molecules are being oxidized.
Meaning they are losing electrons.
Yes. And the oxygen molecules in the air are being reduced, meaning they are gaining those electrons.
So it's an aggressive swapping of atomic material.
Very aggressive. And during this violent atomic swap, the molecules don't just, elegantly reform into ash and smoke.
They don't.
No, they are temporarily broken down into highly unstable intermediate fragments.
Okay, and what are those fragments?
The most critical of these are called hydroxyl radicals. You will often see them written chemically as OH radicals.
OH radicals.
Right. One oxygen atom, one hydrogen atom with an unpaired electron that makes them incredibly reactive.
Now, this is the part that blows my mind. These hydroxyl radicals are the engine of the fire, but they exist for an extraordinarily brief period.
Extraordinarily brief.
We are talking about an existence of just 1 millisecond.
1 millisecond.
1,000th of a second before they react again and are destroyed.
It is an incredibly fast lifespan. They are born, they violently react with another molecule to release energy and create another radical, and then they die.
All in 1 millisecond.
Yes.
So I have to challenge this logic because visually it just doesn't intuitively compute.
What do you mean?
If I'm standing in front of a massive raging chemical fire at a refinery, the flames are 10 stories high. The heat is melting steel.
Right.
How can a chemical reaction that only lasts for a single millisecond possibly sustain a multi-ton industrial inferno?
Well, you're touching on the exact reason we call it an uninhibited chain reaction.
Okay.
It is not one radical doing the work. It is happening billions, perhaps trillions of times per second.
Trillions,
constantly propagating itself in a three-dimensional space. That 1 millisecond lifespan of a single hydroxyl radical is just one microscopic link in an endless exponential chain.
Oh, I see. So one radical dies, but its death creates 2 more.
Exactly.
And those 2 create 4.
It is a self-sustaining loop. As long as the fire still has its 3 base ingredients, the fuel vapor, the oxygen, and the residual heat, those radicals are continuously created and destroyed.
Wow. So the massive energy release we see as a towering visible flame, the heat that melts steel, is just the cumulative result of trillions of these 1 millisecond reactions happening simultaneously.
That's exactly it.
It is a continuous self-sustaining loop of microscopic explosions.
Yes.
That paints a completely different picture of a fire. It's not a single entity, it's a swarm.
A swarm is a perfect word for it.
And this discovery, moving from the triangle to the tetrahedron, identifying that 1 millisecond hydroxyl radical, how did that change the game for safety professionals and firefighters?
It completely revolutionized the entire field of fire suppression technology.
How so?
Think about the historical limitations. If you only operate under the fire triangle model, you believe your only 3 options for fighting a fire are to cool it down with water, smother it with foam or a blanket to remove the oxygen, or somehow starve it by turning off the fuel valve.
Right. These are all physical actions against the environment.
Exactly. But once you understand the fire tetrahedron, you realize you have a secret weapon.
Which is?
You can attack the fourth leg directly at the molecular level.
Wow. Okay.
We began developing chemical agents like halon systems in aviation or specific dry chemical powders that are designed to specifically intercept and interrupt that chain reaction.
So how does a chemical agent actually stop a radical? Does it just get in the way?
It aggressively scavenges them.
Scavenges them.
Yeah, so when a dry chemical like monoammonium phosphate is discharged into a flame, the heat of the fire causes the powder to break down and release its own reactive fragments.
Okay.
These fragments specifically hunt down those 1 millisecond hydroxyl radicals and bond with them before the radical has a chance to react with more fuel.
You are chemically castrating the fire.
Exactly.
You are stopping the formation of the next link in the chain.
And the incredible part is what happens to the environment.
What happens?
When these chemical agents interrupt the chain reaction, the fire still has plenty of fuel sitting there. The room is still full of oxygen.
And the machinery is still piping hot.
Right. But the visible flame drops out instantly.
Instantly.
Instantly. The chemical engine driving the fire is shut down because it cannot sustain its molecular loop.
It's like pulling the spark plug out of a running engine.
Yes.
The gasoline is in the cylinder, the air is in the intake, the engine block is hot, but the combustion cycle is fundamentally broken.
Mm-hmm.
The car stalls.
That is the perfect way to look at it.
That's wild.
And this deep molecular understanding brings us directly to how safety professionals have to divide their daily strategy.
Okay, let's get into that.
Because you can't rely on pulling the spark plug every time. You have to manage time and action on a timeline. This is the temporal divide, prevention versus protection.
This is a huge conceptual shift for the ASP exam.
Yeah.
And honestly, this is for surviving in this industry. We know the two physical models. The triangle for initiating, the tetrahedron for sustaining. Now let's look at how you apply those models in time.
So if we pull back to view a facility's entire safety management system, fire prevention is entirely proactive.
Proactive.
It lives firmly in the world of the fire triangle. Your primary goal as a safety professional designing a prevention program is to ensure that fuel, oxygen, and heat never get the opportunity to meet in the same physical space.
So going back to our cake analogy, prevention is keeping the flour in the pantry, the eggs in the fridge, and the oven turned off.
Exactly. You control the fuels through proper chemical segregation, flammable storage cabinets, and rigorous housekeeping.
Right.
You control the oxygen sources through engineered ventilation or inerting tanks with nitrogen. And you control the heat sources by managing hot work permits, banning open flames, and grounding equipment to prevent static electricity.
You are dictating the terms of the environment before the hazard can materialize.
Yes.
Okay, so what about protection?
Fire protection, on the other hand, is entirely reactive.
Reactive.
It assumes that despite your world-class prevention program, human error or mechanical failure will eventually occur.
Because it always does.
Always. It assumes a fire will start or has already started. Here, you are operating in the brutal world of the fire tetrahedron, and your focus shifts entirely to extinguishment and survival.
I want to push back on this terminology, though.
Sure, go ahead.
Are prevention and protection just semantic safety jargon designed to make procedures look thicker?
Definitely not.
But think about it. If I am a facility manager and I spend $100,000 installing a state-of-the-art sprinkler system in my warehouse, am I preventing a disaster or am I protecting the building? Because to a layperson, those feel like the exact same thing.
It is a critical distinction that dictates how you allocate resources, and it is certainly not just semantics.
Okay, explain.
When you install that expensive sprinkler system, you are engaging strictly in fire protection. Think about the mechanics of a sprinkler head. It sits on the ceiling, completely passive. It does absolutely nothing to stop a forklift from puncturing a drum of solvent next to a sparking grinder.
Right. It can't jump down and stop the forklift.
Exactly. It cannot prevent the fire.
It's just plumbing until something goes wrong.
Yes. A standard closed-head sprinkler only activates once the ambient air temperature at the ceiling. The heat leg of the triangle reaches a specific physical threshold.
Like what temperature?
Let's say a common temperature rating of 155 degrees Fahrenheit.
Okay.
The heat melts the fusible alloy link or shatters the glass bulb holding the water back.
Right.
But by the time that physical threshold is reached and the water begins to flow, the fire has already been burning for minutes.
Oh, wow.
The 1 millisecond chemical chain reactions of the tetrahedron are already raging in the thousands.
The cake is already in the oven and baking.
Baking fast. The sprinkler's job is not prevention. Its job is to dump massive amounts of water onto the fuel to rapidly absorb thermal energy, thereby ripping the heat leg out of the tetrahedron to kill the sustained reaction before the building collapses.
That makes the temporal timeline so clear. Prevention is the hot work permit you issue to the maintenance crew, requiring them to use spark-proof tools and clear combustibles from a 35-foot radius.
Yes.
And protection is the sprinkler system that saves the structural steel of the building if the maintenance crew decides to ignore the permit and use an angle grinder next to a cardboard recycling bin anyway.
Exactly. And as a safety professional, your facility design must incorporate both of these concepts robustly and independently.
You can't just pick one.
No. You can never let an executive tell you, we don't need a strict hot work program, we have sprinklers.
Right.
Because once that protection phase begins, once the chain reaction starts and you rely on the sprinklers, the environment inside that building degrades at a terrifying speed.
Let's talk about that degradation, because the visible flame isn't the only killer.
Not at all.
Once that chain reaction kicks off, the combustion process immediately begins producing highly toxic byproducts.
Right.
Smoke is not just an irritant that makes your eyes water.
Smoke is a lethal, complex chemical cocktail.
What's actually in it?
When materials burn, especially the synthetic plastics, foams, and polymers found in modern industrial facilities, they don't burn cleanly. The incomplete combustion produces a massive volume of gases and particulates.
Like what?
You are dealing with carbon dioxide, raw unburned carbon particulates, hydrogen cyanide from burning plastics, and most dangerously, carbon monoxide.
Carbon monoxide? It's the silent assassin of the fire world.
It really is.
Why is it so uniquely dangerous to human physiology during a fire response?
It comes down to how our blood transports oxygen. Hemoglobin is the protein in your red blood cells responsible for carrying oxygen from your lungs to your organs.
Okay, so it's the oxygen delivery system.
Yes, and carbon monoxide has a chemical affinity for hemoglobin that is roughly 200 to 250 times greater than oxygen.
So if an oxygen molecule and a carbon monoxide molecule are both competing for a seat on the hemoglobin bus,
the carbon monoxide shoves the oxygen out of the way every single time.
Every time?
Every time. It binds tightly to the hemoglobin, forming carboxyhemoglobin, which physically blocks oxygen from attaching.
Wow.
So even if the fire is relatively small, or if your sprinkler system successfully extinguishes the visible flame within a few minutes, the resulting smoke plume can rapidly asphyxiate workers in adjacent areas.
They are breathing in air, but their blood is incapable of delivering oxygen to their brain.
Yes, it's terrifying.
This circles back perfectly to why the proactive fire triangle is so vital. Prevention is the primary goal, because the consequences of relying on protection are just too steep.
Exactly.
Even a successfully extinguished fire can result in mass casualties from the toxic byproducts.
Which means we have to double down on our understanding of how fires actually start in the air. We have to master the invisible physics of the room.
Right. So to truly prevent that initial spark from finding fuel and oxygen, we have to talk about how these elements physically mix in the atmosphere.
Okay, yeah. Let's do that.
Because it's not a binary state. Simply having a fuel source and an oxygen source in the same room does not guarantee a fire.
No, it doesn't.
I mean, I can have a 5-gallon bucket of gasoline sitting open in a garage, the vapors are evaporating into the air, the oxygen is present, but it doesn't just spontaneously erupt into flames.
It requires a highly specific physical ratio. And this brings us to one of the most mathematically critical, highly testable concepts for the ASP exam.
Oh, I bet.
And honestly, the concept that will govern a huge portion of your daily hazard assessments, the flammable range, also known as explosive limits.
I have always visualized this as the Goldilocks zone of destruction.
That's a good way to put it.
For a fire or an explosion to propagate through the air, the mixture of fuel vapor and oxygen cannot be too lean, it cannot be too rich, it has to be mixed just right.
All right.
Let's unpack these limits, because they are the invisible boundaries of life and death.
The primary terminology you will see on the exam blueprints and stamped on the side of every gas monitor in the field is LEL and UEL.
Lower explosive limit and upper explosive limit.
Right. In some texts or regulatory standards, you might see them referred to as LFL and UFL, substituting flammable for explosive.
Or are they different?
For all practical purposes in this context, they are used interchangeably.
Okay, let's start at the bottom boundary, the LEL.
The LEL is the absolute minimum volume or concentration of a combustible vapor or gas in the air that is physically capable of burning or exploding if an ignition source is introduced.
So it's a percentage.
Usually, yes, this is expressed as a percentage of the total air volume. If the gas concentration is below the LEL, we say the mixture is too lean.
Too lean.
To put a physical picture to too lean, think of trying to start a campfire using just one tiny dry twig while standing in the middle of a hurricane.
I mean, there's an infinite supply of oxygen from the wind.
Exactly. But the fuel is so incredibly sparse that even if you get the twig to spark, the thermal energy dissipates into the massive volume of surrounding air before it can heat up and ignite a second twig.
It can't catch.
Right. The molecules of fuel vapor are physically spaced too far apart in the air for the 1 millisecond chain reaction to jump from one molecule to the next. The fire literally starves to death amidst a sea of oxygen.
That is a brilliant way to visualize it. The chain reaction breaks because the links are too far apart.
Yes.
And on the complete opposite end of the spectrum, we hit the ceiling, the UEL, the upper explosive limit.
The ceiling, right.
This is the maximum percentage of fuel vapor in the air that will ignite. If the concentration of gas goes above the UEL, the mixture is considered too rich.
In a too rich scenario, the atmosphere is saturated with fuel vapor.
Saturated.
There is so much gas packed into the space that it physically displaces the oxygen in the room.
Ah, I see.
Without sufficient oxygen to undergo the reduction process, the chemical chain reaction cannot occur.
It's like a teenager learning to drive a manual transmission car and completely flooding the engine.
Exactly like that.
You pump so much raw gasoline into the cylinder that there's no room left for the air intake. You turn the key, the spark plug fires, but the engine just chokes and stalls because it can't breathe.
That is the exact mechanical failure happening at a molecular level above the UEL.
So the flammable range is that terrifying boundary between the LEL and the UEL.
Yes.
This is the valley of death. If you have an atmospheric concentration sitting anywhere inside this range, and a worker drops a wrench or unplugs a radio, or even just shuffles their feet on a dry day and generates a static spark,
a rapid, violent spread of flame or a concussive explosion will absolutely occur.
boom.
And monitoring the invisible boundaries of this range is a massive part of a safety professional's daily operational job.
It has to be.
Whenever workers are entering confined spaces like tanks or sewers, or whenever maintenance is performing hot work near chemical processing areas, you are deploying combustible gas detectors.
These are the handheld meters that sample the air in real time.
Exactly.
But there's a quirk to how these meters read that trips up a lot of new safety folks.
Yes, there is.
A standard combustible gas meter doesn't just tell you the raw percentage of gas in the room. It typically reads on a scale from 0 to 100% of the LEL.
Right.
Why do we read a percentage of a limit instead of just the raw concentration?
It's a psychological and operational safety buffer. As a safety professional, you do not want your workers waiting until the environment actually hits the lower explosive limit to take action.
Because if your meter reads 100% of the LEL,
You have failed. You are actively standing inside an explosive atmosphere.
the bomb is armed.
Right. By configuring the meter to read a percentage of that lower boundary, the device gives you a runway to react.
Okay, that makes sense.
Most industrial alarms on these personal monitors are set to trigger well before reaching the actual danger zone. You typically set a low alarm at 10% of the LEL and a high evacuate immediately alarm at 20% of the LEL.
Let me make sure I'm doing the math right here. If a chemical has an LEL of 5% by volume in the air, your meter alarms when the room hits just half of 1% raw volume.
Exactly. It starts screaming at you while you're still firmly in the too lean zone, warning you to stop work, turn on the exhaust fans, or evacuate long before the atmosphere becomes capable of sustaining a fire.
It is the ultimate proactive tool. It keeps you mathematically locked out of the Goldilocks zone.
That's the goal.
Okay, I have a theoretical challenge for you, and I see this debate happen in facilities when people start looking at the math too closely.
All right, lay it on me.
Let's say I am managing a massive chemical storage tank. The vapor space inside the top of that tank is highly concentrated. Let's say it's 80% raw vapor.
Okay.
It is vastly above the UEL. The environment is too rich to burn. Technically, mathematically, it cannot ignite.
Right.
So would a safety professional ever intentionally choose to leave an environment above the UEL as their primary method of hazard control? Is too rich considered safe?
It is a phenomenal theoretical question, and the practical answer is absolute. Relying on an atmosphere being above the UEL as a primary safety control is an incredibly dangerous, ill-advised, and frankly reckless strategy.
Why? If the physics state it cannot burn, why isn't it a valid control? I mean, I'm saving money on ventilation.
Because the world outside of a textbook is not a static, perfectly sealed laboratory.
Fair point.
The real world is messy. Air moves. Barometric pressure changes. People make mistakes.
True.
If you are deliberately maintaining a room or a vessel above the UEL, what happens the moment a worker opens a bay door or opens a hatch on that tank?
Fresh air rushes in.
An immediate, massive influx of ambient oxygen. That oxygen immediately mixes with your 80% raw vapor.
And dilutes it.
As the fresh air dilutes the rich mixture, the concentration of the gas drops. It drops straight down from the too rich zone, crosses the threshold of the UEL, and lands directly into the explosive flammable range.
Oh, wow.
Yeah.
So by trying to clear the gas, you actually arm the bomb.
Exactly.
You transition an environment from too rich to burn to highly explosive in a matter of seconds, just by opening a door.
You are intentionally engineering a ticking time bomb and waiting for a draft of wind to set it off.
That is insane.
And beyond the explosion hazard, we have to talk about industrial hygiene.
Right.
Any atmosphere that is concentrated enough to be above the upper explosive limit for an industrial solvent or gas is going to be acutely toxic.
Because you can't breathe it.
It will be immediately dangerous to life and health, IDLH, from a respiratory standpoint. Your workers would be fatally poisoned by the chemical fumes long before they had to worry about the fire hazard.
Okay, that makes perfect sense. You're walking a very narrow, very high tightrope, and if you slip, you fall right into a disaster.
Yes.
You never want to manage a hazard by staying above it.
Never.
Yeah.
You mitigate by staying far below the LEL with massive ventilation, or by removing the oxygen entirely using an inert gas like nitrogen in closed systems, which is a specialized process called inerting.
Okay, understood. Now, to make this even more complex for our ASP candidates, we have to talk about how these limits are not carved in stone.
They certainly are not.
The LEL and UEL of a specific chemical are not static numbers that apply universally in all conditions.
No, they are physical boundaries that can be warped and shifted by environmental factors, specifically temperature and pressure.
This is where we bring in the classical physics that dictate our reality. You have to have a solid working grip on Boyle's law and Charles's law, not just for the exam, but to understand how a summer day in Texas changes the hazard profile of your facility.
It's vital.
Let's start with Boyle's law. How does pressure manipulate a gas?
So Boyle's law states that if you keep the temperature constant, the volume of a given quantity of gas varies inversely with the pressure applied to it.
Let's translate that into safety reality.
Imagine you have a set number of gas molecules inside a sealed compressor tank. If you artificially increase the pressure inside that tank, you start squeezing the gas, the volume it occupies decreases. You are physically forcing those gas molecules closer and closer together.
Okay, so if the molecules are being shoved closer together, how does that impact the lower explosive limit?
Remember our campfire and a hurricane analogy?
Yeah.
The LEL is the point where the molecules are close enough for the chain reaction to jump from one to the next. If you use mechanical pressure to shove the molecules closer together, it takes less of the chemical to achieve that necessary proximity.
Oh, I see.
Increased pressure lowers the LEL. The chemical becomes easier to ignite at lower concentrations because you've done the work of packing the molecules tightly for the fire.
That is a terrifying realization.
It is.
If I am monitoring a pressurized vessel, the standard LEL printed on the safety data sheet might no longer be accurate. The bomb can go off sooner than the paperwork says.
Exactly. And temperature plays a similar distorting role. This is Charles' law.
Okay, Charles' law states that gases increase in volume as temperature rises. The textbook definition is that they expand by a specific mathematical fraction for every degree Celsius.
Right.
But how do we visualize that without doing advanced calculus?
Think of the gas molecules like people standing in a crowded, very cold room. Everyone is shivering, standing still, taking up very little space. That's a cold gas.
Makes sense.
Now, turn the thermostat up to 110 degrees. People start getting uncomfortable. They start shifting, moving around, pushing away from each other to get some breathing room.
They need more space.
They become energetic and expand to fill more volume.
So heating a gas pumps it full of thermal energy.
Mm-hmm.
The molecules are literally vibrating faster and spreading further apart.
Now, apply that energy to the flammable limits.
Okay.
If you have a chemical inside a metal tank sitting in a Texas shipyard in July, the sun is beating down on it all day, you are preloading those gas molecules with immense thermal energy.
Right.
Because they are already hot and energetic, it takes significantly less ignition energy from a spark to push them over the edge into a chain reaction.
So extreme heat widens the flammable range.
Yes.
It can lower the LEL and raise the UEL, stretching the boundaries of the Goldilocks zone and making the environment far more volatile.
The parameters of your hazard physically shift based on the weather or the industrial process conditions. You cannot rely on static assumptions.
Which brings us perfectly to two other critical temperature-based definitions that people constantly mix up.
Flashpoint and auto-ignition.
Yes. If temperature can shift the limits, we need to know at what temperature the chemical actually becomes a threat. We need to define flashpoint and auto-ignition temperature.
These are frequently confused, even by seasoned professionals, but they are incredibly distinct concepts with entirely different mitigation strategies.
Let's start with flashpoint.
The flashpoint is the lowest temperature at which a liquid substance vaporizes fast enough to form an ignitable mixture in the air directly above its surface.
So the flashpoint is the temperature where the liquid finally generates enough vapor to hit its own LEL.
Exactly.
If a liquid is sitting in a room that is below its flashpoint, it might smell bad, but it isn't giving off enough vapor to sustain a flame.
Correct. Diesel fuel, for example, has a relatively high flash point, usually above 100 degrees Fahrenheit.
Okay.
If you toss a match into a bucket of cold diesel on a winter day, the match might actually just go out. The diesel isn't vaporizing enough to ignite.
Wow. But gasoline is different.
Gasoline has a flash point of negative 45 degrees Fahrenheit. It is constantly off-gassing explosive vapors in almost any habitable temperature on Earth.
But the key word with flashpoint is that it still requires a spark.
Yes.
If a chemical reaches its flashpoint, it doesn't just spontaneously erupt. It simply means the bomb is armed.
Yeah.
It still needs that external heat source from the fire triangle, a welding spark, a dropped cigarette, a static discharge to actually flash.
It needs an initiator.
Yes.
And that is where the second definition, auto-ignition temperature, becomes the ultimate nightmare scenario.
How does auto-ignition differ?
The auto-ignition temperature is the temperature at which a material will spontaneously combust entirely on its own without the presence of an outside spark or flame.
So no match, no static shock, no dropped wrench.
Nothing. The ambient thermal energy of the environment itself is so high that it initiates the 1 millisecond hydroxyl radical chain reaction simply by existing.
Let's put a real-world scenario to this.
Yes.
Say you have a chemical manufacturing facility with a massive thermal oil heating system or a reactor vessel. The temperature control valve fails, and the system experiences thermal runaway.
The heat inside the vessel starts skyrocketing.
Right. If the chemical inside hits its auto-ignition temperature, the heat of the metal walls itself becomes the match.
The entire volume of the chemical will spontaneously erupt into flames simultaneously from the sheer thermal stress. You don't need a stray spark. The environment itself is the ignition source.
Which is why understanding these four metrics, LEL, UAL, flashpoint, and auto-ignition, is the absolute foundation of your job.
Absolutely.
They're the numerical boundaries of disaster. You have to monitor the LEL to keep the vapors lean, you track the flashpoint to know when a liquid becomes a vapor threat, and you engineer temperature controls to ensure you never even approach the auto-ignition limit.
It is a constant juggling act of chemistry and physics.
Okay, so the rules, we just spent 20 minutes discussing the LEL, the UEL, the gas detectors, the ventilation. They work beautifully and predictably for gases and vapors.
Right.
You can measure a gas, you can exhaust it through a fan, you can predict its behavior based on Charles' law. But here is where the physical reality of the industrial world takes a hard left turn.
We have to examine the terrifying exception to these rules.
We have to talk about combustible dust.
If we look at the history of industrial disasters, combustible dust is arguably one of the most misunderstood and insidious threats a safety professional will ever face.
It defies the logic of gas.
It really does.
Why? Why does dust act so differently than a vapor?
Because the physical state of the fuel fundamentally changes how it interacts with the environment.
Okay.
We aren't dealing with a gas that disperses homogeneously and evenly into the air. We are dealing with solid microscopic particles that have physical mass.
So gravity plays a role.
They are governed by gravity and turbulence, not just thermodynamics.
So the metrics we use to measure them have to change. The texts outline MEC, MIE, and MIT for dust. Let's translate those from textbook jargon into field reality.
Let's start with MEC, minimum explosible concentration.
What is that?
This is the dust equivalent of the lower explosive limit, the LEL. It is the minimum concentration of a combustible dust dispersed in the air, usually measured in mass per volume, like grams per cubic meter, that will support an explosion.
So just like a lean gas, if there isn't enough dust actively floating in the air, the physical distance between the dust particles is too vast.
Exactly. The heat of one burning particle can't bridge the gap to ignite the next particle. The chain reaction starves.
The particles have to be close enough to propagate the flame front.
Right. Next is MIE, minimum ignition energy.
Okay.
This is a critical metric for safety professionals. It is the lowest amount of electrical or thermal energy required to ignite the most sensitive possible mixture of that specific dust cloud.
Give me a practical example of ignition energy. What kind of energy are we talking about?
We measure it in millijoules. It is an incredibly tiny amount of energy.
How tiny?
To give you perspective, if a worker is walking across a facility floor wearing ungrounded boots on a dry winter day, the simple friction of their boots can build up a static charge on their body.
Just from walking?
Just from walking. When they reach out and touch a metal handrail, that tiny invisible static shock they feel, jumping from their finger, often contains tens of millijoules of energy.
A static shock from a finger.
For many highly combustible dusts, like certain fine powdered sugars, metal dusts, or pharmaceuticals, the minimum ignition energy is less than 10 millijoules.
Wow.
That tiny static shock from a worker's finger contains double or triple the energy required to detonate a dust cloud.
That is horrifying. You don't even need a faulty electrical panel. A human being walking normally can be the detonator.
Yes. And finally, we have MIT, minimum ignition temperature of a dust cloud. Similar to auto-ignition for a gas, this is the lowest temperature of a hot surface, like an overheating conveyor belt motor, a seized bearing, or even an unapproved light fixture that will cause a suspended dust cloud to catch fire just by contacting the hot surface.
Okay, so MEC, MIE, and MIT, they parallel the gas limits. But here is where the traditional logic of vapors completely fails us.
Right.
And where safety professionals get into serious trouble if they try to apply gas logic to dust. We talked earlier about the UEL, the upper explosive limit, and how a gas mixture can become too rich to burn.
The flooded engine analogy.
Right. With combustible dust, that concept is practically a deadly myth.
A deadly myth.
The literature is very explicit about this. While a theoretical upper explosive limit technically exists for dusts suspended in the air in a laboratory setting, in the real world, it is highly imprecise and completely irrelevant for safety.
Totally irrelevant.
The sources reference a specific, frankly shocking test regarding dust explosibility. They wanted to see if they could make a dust environment too rich to burn. They placed a spark source inside a blender, and they filled the blender 75% full of combustible dust.
75% full.
It was absurdly dense. It was packed with fuel, practically choking out all the available air in the container.
Yeah.
By all traditional gas logic, it should have stalled. It should have been way past the UAL. They turned it on, introduced the spark, and it exploded violently.
A blender 3/4 full of solid dust can still explode.
When you hear that, you have to ask yourself, how does a safety professional even begin to mitigate a hazard that openly defies the standard too rich rule?
That is the core question. Why does dust behave so erratically? Why doesn't it flood the engine?
Why doesn't it?
It comes back to the physical mass of the particles and the chaos of turbulence. Gas and vapor mix somewhat evenly in a room. If a room is at 50% LEL, it's generally 50% LEL everywhere in the room.
Okay.
Dust does not behave that way. Dust particles have weight, they settle, they fall out of the air and accumulate on rafters, on top of ductwork, on the ledges of machinery, and in the crevices of the floor.
It's just sitting there accumulating quietly over months or years. It's an invisible, dormant bomb spread across the entire facility.
And this is the anatomy of a catastrophic secondary dust explosion, which is what levels factories.
Secondary.
You have all this dust settled quietly. Then an initial, relatively small event happens. Maybe a tiny pile of sawdust near a hot bearing catches fire, or a small pressure release from a machine goes poof.
A primary event.
That primary poof might not even hurt anyone, but the pressure wave from that small explosion travels through the building at the speed of sound. It shakes the rafters, it rattles the ductwork, and it kicks all of that accumulated, settled dust back into the air simultaneously.
It creates a massive, facility-wide, suspended cloud of fuel in a fraction of a second.
And because the dust is highly dynamic, the particles are swirling, falling, clumping together in the turbulent air. The concentration of the dust cloud is completely chaotic. In 1 cubic foot near the ceiling, it might be too dense. 6 inches to the left, it might be below the MEC. But because it is constantly shifting in the turbulence, you are mathematically guaranteed that somewhere inside that massive cloud, the optimal, perfect, explosive mixture of fuel and oxygen exists.
The turbulence creates thousands of localized Goldilocks zones.
And the residual heat from the primary poof ignites those zones.
Wow.
The flame front tears through the facility using the swirling dust like stepping stones, resulting in a devastating secondary explosion that blows the roof off the building. You can never rely on the concentration being too rich to burn because the dust is always moving.
So the safety application here for our listeners is absolute. The texts state this with zero ambiguity.
Yes, they do.
In stark contrast to gases and vapors, seeking to maintain safety by intentionally operating with dust concentrations above the UEL is absolutely not a viable legal or safe approach.
It is a death sentence for a facility.
Just what do you do?
You cannot manage dust by trying to keep the air too dirty to burn. You manage combustible dust through relentless, obsessive housekeeping. You use specialized industrial vacuums, you design machinery with dust collection systems, and you engineer the facility to have smooth surfaces so dust can't accumulate on rafters.
If you see dust accumulating on surfaces thicker than a standard paperclip, which is the classic OSHA visual metric, you already have a catastrophic secondary explosion hazard on your hands.
It emphasizes a foundational truth for safety professionals. Knowing the physical state and chemical nature of your fuel dictates every single tactical decision you make.
Which provides a seamless transition into the final leg of our deep exploration, knowing your enemy.
Yes.
We spent the last 40 minutes establishing the absolute mechanics of fire. We know how it starts with the triangle, how it sustains itself with the 1 millisecond hydroxyl radicals of the tetrahedron, the atmospheric limits it requires to breathe, and the terrifying physics of combustible dust.
Right.
Now, we have to look at the physical fuels themselves.
Because as a safety professional responding to an emergency or designing a suppression system, the specific categorization of the fuel dictates your exact weapon of choice.
And if you choose the wrong weapon,
you don't just fail to put out the fire, you can cause a secondary catastrophe.
This is the practical, boots-on-the-ground application of everything we've discussed. Fires are classified into distinct categories based on the fuel being consumed.
And for the ASP exam and for your career, you must know these classes with instant reflexive recall.
Let's start with the most common Class A.
Class A fires involve ordinary, everyday combustibles. We are talking about wood, paper, cloth, rubber, and many types of standard plastics.
Okay.
If you can throw it in a traditional campfire and it leaves behind an ash, it is likely a Class A fuel.
The classic trash can fire or pallet fire. And the standard universal strategy for extinguishing a Class A fire is water.
Yes.
But let's elevate this beyond just memorizing a chart. Let's look at why water is so devastatingly effective against Class A fuels, connecting it back to our fire tetrahedron.
Water is a miracle extinguishing agent for ordinary combustibles because it has a tremendous specific heat capacity.
Meaning what?
It takes a massive amount of thermal energy to raise the temperature of water and even more energy to convert it from a liquid to a gas to boil it into steam.
So when you spray a hose onto a burning pallet of wood, what is happening at the molecular level?
The liquid water coats the porous surface of the wood. The intense heat of the fire is immediately absorbed by the water. As the water absorbs the heat, it flashes into steam.
Right.
The physical expansion ratio of water to steam is roughly 1,700 to 1.
1,700 to 1.
Yes. 1 drop of water violently expands into 1,700 drops of steam volume.
So 2 things are happening. First, the water is violently ripping the thermal energy out of the wood to boil itself, removing the heat leg of the tetrahedron.
Yes. And second, that massive 1,700 to 1 expansion of steam creates an inert cloud of water vapor that pushes the ambient oxygen away from the surface of the fuel.
Wow, it simultaneously cools and smothers.
Exactly. Without the heat to continue vaporizing the wood, the fuel stops off-gassing, the 1 millisecond hydroxyl radicals stop forming, and the chain reaction collapses.
It is an incredibly elegant physical attack.
It really is.
Now let's pivot to a class where water goes from being a miracle cure to a lethal hazard. Let's look at Class C fires.
Class C fires involve energized electrical equipment.
Okay.
We are talking about live wiring, breaker panels, motor control centers, and high-density data server racks.
These are particularly tricky from a hazard recognition standpoint because they rarely happen out in the open.
Right. They often initiate in hard-to-reach or hidden locations, a degraded wire short-circuiting behind a sealed panel, or a power surge overheating a transformer.
And this is the scenario where a well-intentioned, poorly trained worker can easily turn an equipment emergency into a fatal human tragedy.
Absolutely.
Walk us through that nightmare scenario. Let's say a worker sees smoke billowing out of a 480-volt electrical panel. They panic. They grab a standard pressurized water extinguisher off the wall, a Class A solution, and they spray a solid stream of water directly into the live electrical fire. What happens physically?
It would be instantaneously disastrous.
Why?
Water, in its natural unpurified state out of a tap or an extinguisher, is full of dissolved minerals, salts, and ions. These impurities make the water highly conductive to electricity.
It is essentially liquid wire.
Exactly. When that worker sprays a solid stream of water onto an energized 480-volt panel, that stream of water creates a physical, unbroken conductive path, bridging the high-voltage source directly to the person holding the extinguisher.
Oh my.
The electrical current travels instantly up the stream of water through the metal casing of the extinguisher into the worker's hands, across their heart, and down through their boots to the ground.
They're violently electrocuted on the spot.
Yes. You didn't just fail to extinguish the fire, you introduced a lethal, immediate shock hazard to the responder.
Which is why hazard recognition and training are so critical. For Class C energized electrical fires, you must use non-conductive extinguishing agents.
Yes.
So what is the tactical approach for Class C?
Carbon dioxide CO2 is a very common and effective choice for localized electrical fires. A CO2 extinguisher blasts a dense, freezing cloud of carbon dioxide gas into the panel.
Going back to the tetrahedron, how does CO2 work?
It attacks a different leg. CO2 is heavier than air, so it physically displaces and pushes the oxygen away from the fire, suffocating the reaction.
Okay.
It also discharges at extremely cold temperatures, providing some rapid cooling of the heat leg, and crucially, it leaves absolutely no residue behind.
Which is vital for expensive electronic equipment.
Exactly, and it is completely non-conductive, protecting the user.
We also mentioned earlier the dry chemical agents, which can be rated for Class C. They work by chemically scavenging and inhibiting the chain reaction without conducting electricity.
Yes. So water for Class A, non-conductive gases or dry chemicals for Class C.
But now we have to enter the truly exotic and terrifying realm of heavy industry. We have to discuss Class D fires.
Class D fires are unique, highly specialized industrial hazards. They involve combustible metals.
Like what?
We are talking about elements like magnesium, sodium, titanium, potassium, or zirconium.
These are not materials you are going to find sitting in a typical office building or a retail warehouse.
No, this hazard is found in heavy manufacturing, aerospace component machining, specialized automotive plants, and recycling facilities.
But when a Class D fire starts, it changes all the rules of engagement. Combustible metals burn at extraordinarily high temperatures, far, far hotter than a standard wood or liquid fire.
Much hotter.
A magnesium fire can easily burn at over 5,000 degrees Fahrenheit. It is blindingly bright white hot.
The thermal energy being released is staggering, and because of that immense heat, your instinctual response using water becomes the most dangerous thing you could possibly do.
Let's play out that scenario, because the chemistry here is mind-blowing. If a worker has a pile of magnesium shavings catch fire on a lathe in a machine shop, and they throw a bucket of water onto that 5,000-degree fire, what happens?
The heat is so incredibly intense that it actually alters the molecular structure of the water itself.
Wait, what?
When the H2O hits the burning metal, the thermal energy is so violent that it physically strips the oxygen atom directly out of the water molecule.
Wait, it breaks the water apart.
It violently separates the hydrogen and the oxygen. The burning metal consumes the oxygen from the water to feed its own oxidation process, making the fire burn even hotter.
That's crazy.
But the terrifying byproduct is what happens to the hydrogen.
Water is H2O. If the fire steals the O, you are left with pure H2, hydrogen gas.
The water hitting the fire is instantly converted into highly explosive hydrogen gas. That hydrogen gas is immediately ignited by the 5,000-degree heat of the burning metal.
So the water literally acts as an extreme accelerant. By throwing a bucket of water on a magnesium fire, you are essentially throwing a bucket of explosive gas directly into a furnace.
It will result in a massive, violent, concussive explosion that throws molten, burning metal shrapnel across the entire facility.
That is the stuff of nightmares. So if water causes an explosion and CO2 won't work because the metal is burning too hot, how do you fight a Class D fire?
Class D fires absolutely require highly specialized dry powder agents.
Dry powder.
Note that we say dry powder, not dry chemical like a standard ABC extinguisher. These powders, often based on sodium chloride or graphite, are engineered not to chemically react with the burning metal.
So how do they extinguish the fire?
When you gently apply a Class D powder onto a burning metal, the immense heat causes the powder to melt. It physically flows over the burning metal and forms a solid, hard crust, almost like a thick shell of glass or salt.
It's like pouring liquid concrete over the hazard.
This crust completely and perfectly seals the burning metal off from the ambient oxygen in the room. You are manually removing the oxygen leg of the tetrahedron, and because the metal is sealed, it allows that massive 5,000-degree thermal energy to slowly, safely dissipate into the crust over a period of hours without interacting with the air.
You are building a physical quarantine shell around the fire.
It requires a completely different mindset, specialized training, and specialized equipment. And this brings up a critical facility design issue for safety professionals.
What's that?
This highlights exactly why hazard recognition and segregation are so utterly critical.
You cannot mix your mitigations.
If you have a machine shop that works with magnesium, you absolutely cannot store those Class D combustible metals in a room protected by standard overhead water sprinkles.
Oh, because if a small trash can fire sets off the sprinkler system in that room.
The building's own automated safety system will spray water directly onto the magnesium, triggering a catastrophic facility-level explosion. Your protection system becomes the weapon of your destruction.
That is the ultimate proof of the thesis we started with today. You cannot just memorize a list of fire extinguishers for the ASP exam.
No, you can't.
You have to deeply understand the molecular chemistry of the fuel, the dynamic mechanics of the tetrahedron, and the unintended deadly consequences of your extinguishment tactics.
If you do not intimately understand the why and the how behind fire physics, the what you decide to do in an emergency can be deadly.
Okay, let's take a deep breath and synthesize the massive journey we've just taken over the last hour. We started at the absolute microscopic level, looking at a single hydroxyl radical that exists for just 1 millisecond, driving the uninhibited looping chain reaction of the modern fire tetrahedron.
Right. And we examined the temporal shift required in a safety professional's daily mindset.
Yes, using the proactive fire triangle to manipulate fuel, heat, and oxygen to prevent a fire from ever starting, versus attacking the tetrahedron to violently interrupt the chain reaction and protect a facility once combustion occurs.
We navigated the invisible, mathematically rigid boundaries of the flammable range.
We looked at how physical pressure, Boyle's law, and thermal energy, Charles's law, can stretch and shift the LEL and UEL, and why that Goldilocks zone must be monitored relentlessly by calibrated gas detectors that give us a safety buffer.
We uncovered the deadly myth of a UEL when it comes to combustible dust, realizing that the physical mass and turbulence of a suspended dust cloud create dynamic, unpredictable hazards that defy the rules of standard gases.
Requiring obsessive housekeeping rather than atmospheric manipulation.
Exactly.
And finally, we classified our enemies. Class A, ordinary combustibles smothered by the massive expansion of steam. Class C, energized electrical threats requiring non-conductive suffocation. And the terrifying water-reactive reality of Class D combustible metals that must be entombed in a crust of dry powder.
It is a massive amount of technical information, but we want to reiterate directly to you, the listener, as you prepare to conquer this 12% chunk of the ASP exam. These are not just textbook definitions.
No, they are the immovable, physical laws of the universe that you have chosen to manipulate, monitor, and master as a profession. Your deep understanding of these absolute fundamentals dictates whether the workers in your facility go home safely to their families at the end of their shift.
It is an incredible, heavy responsibility.
And before we close out this QHSE Talks, I want to leave you with a final provocative thought to ponder as you continue your studies and walk your facility floors.
Okay.
We've spent an hour talking extensively about the traditional classes of fire and our current understanding of the fire tetrahedron.
Frameworks that have fundamentally been based on fuels that have been around for a century. Wood, gas, oil, basic metals.
Exactly. But look at the trajectory of the industrial world today. Manufacturing is rapidly introducing entirely new, hyper-complex synthetic polymers and materials into our supply chains.
Yes.
More importantly, we are aggressively transitioning to green energy fuels. We are building massive lithium-ion battery storage farms, electric vehicle manufacturing plants, and utilizing exotic chemical processes for renewable energy.
We are changing the fuel of the world.
As these unprecedented high-density energy sources become commonplace, How will the traditional classes of fires and our fundamental strategies for breaking the tetrahedron have to evolve in the next decade to keep pace?
Yeah, it's a great question.
When a lithium-ion battery goes into thermal runaway, creating its own oxygen and burning with chemical intensity that laughs at traditional extinguishment, are we on the verge of needing a Class E or Class F? Will you be the generation of safety professionals that has to pioneer entirely new extinguishing physics?
It is a phenomenal question that every forward-thinking safety professional should be asking themselves right now, because the fuels are rapidly changing, but the devastating primal power of the fire remains exactly the same.
Something critical to mull over as you prep for your exam and look at your own facility's future. Thank you for keeping learning with QHSE Talks.